Hello! In this video, I'd like to tell you a story about continuity at a point. When I was covering continuity in one of my Calc 1 classes, one of my students asked me a very sensible question. Is the square root of x continuous at x equals 0? The difficulty being, of course, that the function isn't defined to the left of 0. We're specifically looking at the real square root function. We're not doing complex numbers in a Calc 1 class. I wasn't sure, so I looked through the textbook, and initially it seemed like the answer was no. The square root function didn't meet the definition of continuity. The usual trinary f of a is defined, the limit is defined, and the two are equal. Because the limit from the left didn't exist, I assumed that the limit didn't exist. But the chapter on continuity didn't say anything specifically about square roots or similar functions, so I looked further and found this. If f of x is a function and the limit as x approaches c of f of x exists, n is a positive integer and the nth root of this limit is defined, then the limit as x approaches c of the nth root of f of x is the nth root of the limit of f of x. Specifically, if f of x is just x and n equals 2, then this is saying that the limit as x approaches 0 of the square root of x is 0, which is odd, but it's consistent with the vague way that limits were defined in the text. So maybe the square root of x function is continuous at x equals 0, or maybe the text was misleading? To get a second opinion, I pulled out a copy of one of the textbooks I TA'd from at Cornell. Thomas's Calculus, a real doorstopper of a text. Their definition of continuity at a point first defines continuity in the interior of the domain of a function, the way that we would expect, right? The limit as x approaches c of f of x is f of c. And then makes explicit exceptions for the left and right endpoints of the domain of the function. According to this, the square root function is continuous at x equals 0, the left endpoint of its domain. And although Thomas's Calculus has exactly the same three-part continuity test, an explicit exception is made for continuity at endpoints. And they even have an explicit example in the text of a function involving square roots with this sort of continuity at the endpoints of the domain. So pretty definitive, right? According to Thomas's Calculus, the square root function is continuous at x equals 0, a left endpoint of its domain. But then why, later on in the chapter, in Theorem 9, Properties of Continuous Functions, point 6, powers, does the text suggest that x to the 1/2 is continuous only at interior points of its domain, right? If f here is x and r over s is 1 over 2, then we're requiring that the square root be defined on an open interval around our point. So only for x strictly greater than 0 does this happen. And then, in example 8, the text goes on to claim that Theorem 9.6 actually does claim that the square root function is continuous at x equals 0. The more I read and the more I thought about this, the more confusing the situation got. Consider the function x sine 1 over x. If we remove the removable discontinuity at x equals 0, the resulting function, let's just call it f, is continuous everywhere. If we then take the square root of f, the resulting function has a lot of large intervals missing from its domain, corresponding to places where x sine 1 over x is negative. If we plug 0 into this function, again we get 0, but x equals 0 falls into none of the categories where Thomas's Calculus defined continuity at a point. X equals 0 is not an interior point of the domain. That is, there isn't an interval around x equals 0 where the function is defined on that entire interval. And it's not a left or right endpoint of the domain of the function. We have a lot of left and right endpoints, but 0 isn't one of them. But theorem 10 in Thomas's calculus says that if f is continuous at c equals 0, and g, the square root function, is continuous at f of c at 0, which the square root function meets the definition of continuous at 0, then the composition is continuous at 0. So is there an entirely separate case of continuity at a point that the text just doesn't mention but is kind of implicitly assuming? It being clear that the situation was hopelessly confused, I assured my student that they wouldn't be assessed on the matter, then filed this in the back of my mind as an oddity that comes up when teaching Calc 1. Until recently, when I stumbled across the paper Defining Continuity of Real Functions of Real Variables by J.F. Harper from 2016. Harper surveyed a wide variety of real analysis texts, comparing their definitions of continuity at a point. This included both the original sources and newer real analysis texts. Harper's paper is really fascinating, detailing the initial struggles of mathematicians to formalize their intuitions of continuity, with some mathematicians providing contradictory information in a single text, or changing their minds from one edition of a text to the next. And the confusion we've seen over continuity at a point comes from this. Ultimately, there seems to be three definitions of continuity at a point that are still in use today. The first is only defined on interior points of the domain of a function. That is, in order for a function f to be continuous at x, not only does x need to be in the domain of f, but also an interval of values to the left and right of x need to be in the domain of f. So in particular, since x equals 0 is not in the interior of the domain of the square root of x, it is not continuous there. Right? If we're looking at any positive x, there's a range of values around this x that are in the domain of the square root function. But if we're looking at x equals 0, we can't find a range of values. It can be as small as we want, and it's still not going to be entirely in the domain of the square root function, because there's no range of values to the left of x equals 0 that are in the domain. Similarly, if we look at our square root of x sine 1 over x function, 0 is in the domain because we filled in a discontinuity, but we can't find a range of values around 0 that doesn't hit lots of these gaps in the domain. So 0 is not in the interior of the domain, so this first definition wouldn't consider this function to be continuous at x equals 0 either. This is a very sensible definition and agrees with what one might write down with epsilons and deltas as the definition of continuity at a point. It also captures the intuition that a function f is continuous at x equals c if whenever we plug in values of x close to c into f, we get values close to f of c. Specifically, if we plug in values of x close to but less than 0 into the square root function, we don't get a value close to the square root of 0, we get undefined, which is in some sense nowhere close to f of 0. The second definition Harper found makes explicit exceptions for left and right endpoints of the domain of a function, as we saw in Thomas's calculus. I really don't like this definition since, as we saw in the case of the square root of x sine 1 over x function, we lose closure under composition if we're only making exceptions for the left and right endpoints of a domain. In order to keep closure under composition, we're somehow going to have to make even more exceptions so as to include x equals 0 on this function here. And the third definition that Harper found does exactly that. It actually ignores all points near c where the function isn't defined. So our square root of x sine 1 over x function would be continuous according to this definition, since if we plug in a value of x near 0 into this function, and we get lucky enough to hit a value where the function is defined, the output is going to be close to 0. And by looking close enough to 0, we can get the output to be as close to 0 as we want. And similarly, if we're looking at the square root function from this perspective, if we plug in a value near 0 into the square root function, where the function is defined, the value that we're going to get back is going to be close to 0. This is also a very sensible definition and corresponds to restricting x in the definition of continuity to be in the domain of f. Right? So we only care that f of x is close to f of c if f of x is actually defined. And the corresponding intuition here is that a function f is continuous at x equals c if whenever we plug in valid values of x close to c into f, we get values close to f of c. This is the sort of definition one might come up with after studying continuity in arbitrary spaces. Instead of viewing the square root function as a function defined on the reals, but it doesn't always have to give us an output, it's allowed to be undefined, so a partial function defined on the reals. Instead of that, we view the non-negative reals, the domain of the square root function, as the entire universe for the moment, right? If the non-negative reals are the entire universe, then it doesn't make sense to talk about plugging in negative reals into our function and getting an undefined output. And so we don't have to worry about plugging negative values into our square root function. What I found quite surprising is that all three of these definitions are still in recent use. Harper found the first in Gowers et al.'s The Princeton Companion to Mathematics from 2008, the second in Carlson's A Concrete Introduction to Real Analysis from 2006, and the third in Bartle and Sherbert's Introduction to Real Analysis from 1992. While it's very understandable that the definition of continuity at a point would be in flux early on, with mathematicians trying to figure out which definition was the nicest, had the nicest properties, one expects there to have been a point where the community settled on a canonical definition. But this point hasn't happened yet. To get a sense of their relative frequencies, Harper surveyed all 55 books at the Victoria University of Wellington published after 1952 that defined continuity on real functions, and found 18 of them used the first type of definition that only applied to the interior of domains of functions. 5 used the second type of definition that made explicit exceptions for left and right endpoints of the domain, and 32 used the third type of definition that ignored points nearby x equals c that weren't in the domain of f. So while there are clear favorites, there's no definitive the definition that the mathematical community uses. I highly recommend going through Harper's survey. I'll link it down below. In fact, this survey inspired me to do one of my own. I've obtained a number of standard Calc 1 textbooks over the years from free book piles and library book sale discards, and I also found a number of texts freely available online. Obviously, this survey is going to be biased, just as Harper's survey was, so just keep that in mind as I go through the data. I started my survey of these Calc 1 textbooks in the chapters on limits, since most of the texts I was working from defined continuity in terms of limits, and so their exact notion of continuity would depend on their exact notion of limit. It seems like the standard now is to require, when taking the limit as x approaches c of f of x, that there be some interval around c where f of x is defined, except possibly at c. But it's also very common for texts to simply not provide any hypotheses. In many of these cases, I classified the text as requiring definition around the point anyway, when the definition was worded in a way that seemed to require f to be defined around the point. Earlier texts, texts from the mid-1900s, had more unusual definitions. I found two that seemed to place no restrictions on the domain of f. Initially, this just seems to be an analog of case 3 for function continuity, the most common case that we saw in Harper's survey. But if one isn't careful, this definition completely falls apart. Here's the definition of limit from Crowell and Sleznick, 1968. Notice that they only care about x in the domain of f. However, if f is only defined at x equals a or not defined at all, then this implication is vacuously true, regardless of the choice of b. We've lost uniqueness of limits. Smale's 1953 text also seems to have the same issue. I'm also counting Brzezinski's text as implicitly not caring if the function is defined around the limit point, although it's really not clear from the wording. So let's say implicitly no requirements on the domain. I also found a few texts, also old, that have an analog of the definition of continuity that makes an exception for endpoints, the second definition that we saw from Harper's survey. These limit definitions require f to be defined to at least one side of the limit point. For instance, in Johnson and Kiyokemeister from 1963, they require either an open interval in the domain to the left or right of the limit point. This is also asking for trouble. One of the theorems we want is for the limit of the sum to be the sum of the limits. But if we're willing to define the limit as x approaches 0 for functions on the non-negative reals and functions on the non-positive reals, then we really want to define the limit as x approaches 0 for their sum, which is only defined at x equals 0, and which this definition here doesn't do. We can work around this by being careful, but neither text I looked at did this. And we'll see a similar issue when we look at continuity at a point. Finally, one text by Finney et al. Either is working from a weird definition of neighborhood or requires f to be defined at c, which kind of breaks the limit definition of derivatives, so I have to assume that they're just working with a non-standard definition of neighborhood. Also, I found a really fun approach taken by Latour et al. In 2012, which was to define left-hand and right-hand limits first, and then use those to define full limits. I'm really kind of surprised that this wasn't in more calculus textbooks. It's very efficient if you're going to define left and right-hand limits anyway. One of the things that really surprised me in my survey was just how many texts gave the epsilon-delta definition of limits. Particularly since when I TA'd Calc 1 at Cornell, we were explicitly told to skip the chapter on epsilonics entirely. In addition to being a really tricky concept, students at this level are usually not used to seeing Greek letters, so that becomes an added obstacle to understanding. I wasn't entirely sure how to classify, if you look at there's wedge B, McCallum and Tromba from 1972. Wasn't sure how to classify it. They have a perfectly formal definition of limits using neighborhoods, something that would be totally acceptable in a real analysis class, but they didn't use the letters epsilon and delta, and they kind of spread out the definition over several sub-definitions so that it was less confusing. So I wasn't really sure how to classify it. We also see that most of the texts put off the epsilon-delta definition until after they first define limits with something more approachable. Also of note that the oldest text I surveyed, Bicyker from 1921, used eta instead of delta. Typically, when a Calc 1 student is working with limits, though, it's with the various limit theorems. They're really not thinking about epsilon-delta. I always feel a little weird teaching them, since they're almost too straightforward. The limit of the sum is the sum of the limits, but also the same for products and quotients and pretty much anything. The limit theorems represent a recursive approach to evaluating limits, kind of working from the outside of the formula in, peeling an onion. And I suppose this is to set up students for using the corresponding derivative theorems. But I'm not sure. I think because the limit theorems are so straightforward, I don't think it's a good way of setting that up. And this really isn't how I tend to think about limits. I much prefer to teach just recognizing when we can plug in and tricks to apply if we can't. But if we're going to do limit theorems, and a lot of these texts do limit theorems, the more limit theorems we have, the better. So it's really tempting to have limit theorems for square roots or arbitrary powers. Here we see Thomas's calculus correctly placing restrictions that prevent their limit laws from saying that the limit as x approaches 0 of the square root of x is 0. Even though Thomas's calculus makes exceptions for left and right endpoints of the domain when talking about continuity at a point, they don't make such exceptions when talking about limits. A fair number of texts simply omitted a limit theorem for roots, focusing on simpler cases like sums and products. I found 4 texts that said that the limit as x approaches 0 of the square root of x was 0 in a way that was consistent with their definition of limit. Mainly these are the older texts, but I'll also count Brzezinski's text from 2021. Johnson and Kiyokemeister's text from 1963, recall, only required the function to be defined on at least one side of the limit point. Also, they used the word limit instead of lim when writing limits, which I found quite amusing. 6 texts had a similar theorem, but restricted to exclude the square root of 0 case, for instance, as we saw in Thomas's calculus. 3 texts had a radical limit theorem that did include the x equals 0 case, but included some sort of caveat to make the theorem true. For instance, requiring the term under the limit to always be positive, or stating that if the limit does exist, and we're making no claims about whether or not the limit exists, it has this particular value. And then finally, 3 texts I found had a radical limit theorem that asserted that the limit as x approaches 0 of the square root of x was 0 in a way that was inconsistent with how limits were defined in the text. Rogowski and Adams from 2015, for instance, claims that the limit as x approaches 0 of the square root of x is 0, despite explicitly requiring the function to be defined around the point when they define limits. Many texts steered away from giving examples of limits involving square roots. As one might expect, I wasn't able to find any texts that gave as an explicit example that the limit as x approaches 0 of the square root of x doesn't exist, even if that's what their definition of limit required. It would be just too confusing for students to give kind of like, you might think that this limit should exist, but for technical reasons it doesn't, as like an example of limits not existing. While I was surveying limit definitions, I also noted how many of the texts demonstrated limits by plugging in a series of closer and closer values to the limit point. I have found such demonstrations in all of the texts that I surveyed except 2, and those 2 are really early texts. And I feel really mixed about this. It's a really good way of giving students a starting intuition, but it can easily give wrong answers due to plugging in the wrong points or issues with numerical precision on your calculator. So I was glad to see a fair number of texts including a warning for students nearby that this method won't always give the correct answer. Stewart 2007 does a really good job of this. They first show an example of guessing a limit by plugging in values closer and closer to 0. Then they show that example falling apart due to numerical imprecision on the calculator when they plug in values that are even closer to 0. But then they also give the example of sine pi over x as x approaches 0, where if we just plug in common values, 1 over n, we're always going to get 0, and so it's tempting to say that the limit is 0, but this function oscillates, so the limit doesn't exist. And so we have both a case where the calculator gives us an incorrect impression due to numerical imprecision, but also where plugging in gives us an incorrect impression even if we get the correct values out of the calculator. But more fundamentally, no finite table of values of a function can tell you anything about any limits. So there's a subtlety about limits that this approach gives a misleading impression about. So now we get to the heart of my survey. How did these various texts define continuity at a point A? Most of them required f to be defined in an interval around A. Oh, hold on. Specifically, most of the texts I surveyed didn't say anything about the domain of f, but because of how limits were defined in the interior of the domain of f, their definition of continuity at a point only made sense in the interior of the domain. Right? These texts are saying that a function is continuous at a point if the limit exists and agrees with the value of the function, and in order to get that limit to exist, because of the way that the text defines limits, it needs to be defined, the function needs to be defined around the point. But they're not making that restriction explicit. I found this sort of continuity definition way more often than it appeared in Harper's survey. But again, we shouldn't jump to any conclusions. Our surveys aren't statistical. Again, most of these definitions, they're not saying anything explicit about the domain of f. 6 of the texts I found made explicit exceptions for continuity at endpoints. Many of which seem to be descendants of Thomas and Finney's text from 1983. And Johnson and Kiyokemeister's text from 1963, again, when they're defining continuity, they just say the limit exists and agrees with the value of the function, but because of the way that they define limits, technically they're making exceptions for endpoints of the domain. A surprising few texts I looked at don't put any restrictions on the domain of f, and neither of them do so explicitly. It's just a consequence of the way that they define limits. And again, that's a little bit strange because that was the case that showed up most often in Harper's survey. But I guess it really isn't surprising that Calc 1 text might steer away from discussions of functions like our square root of x sine 1 over x function, which have domains with lots of gaps in them. These aren't the kinds of things students are likely to encounter in a Calc 1 class. Now, I should note that it's entirely possible that I got some of these classifications wrong. The definition of continuity at a point, as stated in Apex Calculus from 2026, requires the limit point to be in the interior of the domain of f. However, later on in the text, they say that if a function is continuous from the right at a left endpoint A of its domain, we can, quote, say that f is continuous at A without ambiguity. So, in some sense, the text is actually making exceptions for left and right endpoints of the domain of f. And this isn't an uncommon phenomenon. A couple of other texts also changed up their definition of continuous to make exceptions for left and right endpoints of the domain when they were defining continuity on an interval. Look at this definition carefully. Is this exception only meant to apply when determining continuity on an interval? It really isn't clear. I interpreted this as modifying the definition of continuity at a point in all cases where I found it. I'll talk more about continuity on intervals later, but a key assumption that I made in the survey is that continuity at a point and continuity on an interval are completely distinct concepts. A text is allowed to define these two concepts however it likes, and I tried not to make any assumptions about how these two concepts were related. Of course, once we have these definitions of continuity at a point, we can compare them to what the text says explicitly about the square root of x. So I went through and checked, looked for theorems and examples that had something to say about the continuity of the square root of x at x equals 0. A lot of the texts don't say anything about the continuity of the square root of x. For many of these, continuity seemed to be a low priority, mentioning just the basic definition and then not going into a lot of detail. A few texts I surveyed said, yes, the square root of x is continuous at x equals 0 in a way that disagreed with their definitions of continuity and limits. 3 such texts I found made exactly the same mistake, and to demonstrate it, I want to work from a specific text by Larson, Hostetler, and Edwards from 1998. First, the text defines limits explicitly requiring the function we're taking the limit of to be defined around the limit point, except possibly at the limit point. According to this convention, the limit of the square root of x as x approaches 0 can't exist, since the square root of x is not defined in an interval around x equals 0. Next, the text defines continuity at a point. In order for condition 2 to hold, in order for the limit of f to exist, f must be defined around x equals c. According to this convention, the square root function can't be continuous at x equals 0 because the limit doesn't exist. Then, the text defines continuous on an open interval as being continuous at each point in the interval. So, a fairly straightforward approach so far. Next, the text defines continuous on a closed interval the way one hopes, by requiring the appropriate left-hand and right-hand limit to agree with the function on the endpoints. So far, so good. And, as the text says, we can extend this convention to any interval. The text even gives the example of the square root function being continuous on the interval from 0 inclusive to infinity. And this is fine. This whole set of conventions that we've seen so far is consistent and sensible. Saying that the square root function is continuous on the infinite interval from 0 inclusive to infinity doesn't imply that the square root function is continuous at x equals 0. It simply implies that we have right continuity at that endpoint. But then at the last moment, the text says, without conditions, that radical functions are continuous at every point in their domains. Had the text said, are continuous on their domains, this would be entirely true. The domain of the square root function is an interval. It's this interval specifically. And so the statement would be invoking the definition of continuity on an interval. But by the way that this is phrased, I interpret this as meaning that for every x in the domain of the square root function is continuous at x. Since 0 is in the domain of the square root function, this is saying that the square root function is continuous at 0, which is not true according to the conventions of the text. And I found 2 other texts that take almost this exact same journey to make almost the exact same error in the end. We also saw a bunch of texts that made an exception for continuity at left and right endpoints of a function's domain. According to their conventions, the square root of x is continuous at x equals 0. So here we have Thomas and Finney, 1983, that does have this endpoint exception convention and does say that, they're saying that y equals the square root of x is continuous, which implies that it's continuous at x equals 0, according to their conventions. I found 5 texts that had those conventions and correctly said that, yes, the square root of x is continuous at x equals 0. Actually, I found 7, but the last 2 were a little unusual. 2 of the texts that I found only demonstrated an opinion on whether the square root function was continuous at x equals 0 in the homework section. What a nightmare. I can easily see this causing frustration for students, having to work this out, having to work out the text's precise conventions on continuity, essentially on their own, or looking up the answers in the back of the book. And then finally, I found a handful of examples where the statement had been modified to be correct. Something like the square root function is continuous on its domain, which again I interpret as invoking the definition of continuity on an interval, since the domain of the square root of x is an interval. Or the function is continuous at x is greater than 0. Actually, this example here from Apostle 1967 is quite hilarious. The text covers integration before talking about continuity and limits, and so can appeal to the fact that root functions are the integral of something, and integrals are always continuous, to conclude that root functions are continuous. This is very silly. I want to take a moment to go back and talk some more about the convention of defining continuity at a point, making explicit exceptions for left and right endpoints of the function's domain. We already saw back at the beginning that this causes problems with closure under composition, but it also causes problems with just basic closure under addition, or really any function operation. Right? This definition of continuity at a point implies that the square root of x and the square root of negative x, its mirror image, are both continuous at x equals 0, because that's an endpoint and they satisfy the appropriate limits. Thomas's calculus then claims that if two functions are continuous at some point, then their sum or difference or product or quotient, this problem happens with all of these, is also going to be continuous at that point. So we should expect that the sum of the square root of x and the square root of negative x will be continuous at x equals 0 as well. But this function here is only defined at a single point. And while there are continuity conventions that allow functions defined at only a single point to be continuous, Thomas's calculus does not make that sort of exception, and I found this error in 6 of the 7 textbooks that made explicit endpoint exceptions. All but one. Apex Calculus from 2026 is one of those confusing texts that first appears to define continuity only on the interior of the domain of a function, but then later on defines continuity at a point for left and right endpoints of the domain as well. Right, if f is continuous from the right at a, and f is undefined for x strictly less than a, we can just say that f is continuous at a without ambiguity. But instead of going on to make the same error Thomas's calculus does, they have a slightly different sum theorem. Let f and g be continuous functions on an interval I, then their sum is continuous on I, and this does work. Trying to define continuity at a point that makes exceptions but only for left and right endpoints of the domain of a function also, as we saw at the very beginning, opens the text up to having an incorrect composition theorem for continuity at a point. All 6 of the texts I found that had an incorrect composition theorem for continuity do so because they made left and right endpoint exceptions. Although, honestly, the big surprise here is how many texts omit a continuity composition theorem entirely, even among those that use compatible conventions. While I was at it, I decided to survey other continuity definitions. My sample was about evenly split on whether or not to define left and right continuity with older texts, generally avoiding such definitions. In some sense, continuity on an interval is one of the key continuity-related definitions in a Calc 1 text. It's possibly the most important, since it forms a key part of the hypotheses of theorems like the intermediate value theorem and extreme value theorem. I collected 4 separate pieces of data about what kinds of intervals continuity was defined on and how it was defined. First, did the text define continuity on closed intervals? This is the one that's key for our continuity theorems. If so, did it only require left and right-handed continuity at the endpoints? I'll explain this further when we get to it. And then, did the text also define continuity for open intervals and half-open intervals? 7 of the texts I surveyed didn't define continuity on an interval at all. One text just defined continuity on open intervals. 5 of the texts defined continuity on arbitrary intervals in a way that was careful about endpoints. As we see, Larson, Hostetler, and Edwards, 1998, defines a function being continuous on a closed interval if it is continuous on the corresponding open interval, which it defines earlier the way you would expect, and we have right-hand continuity at the left endpoint and left-hand continuity at the right endpoint. With this definition, we only care about what's happening with the function on the interval, not nearby. Consider, for instance, the function which is 1 on the closed interval from 0 to 1 and 0 elsewhere. This function might be discontinuous at 0 and 1, but it's constant on the closed interval from 0 to 1. So I really want to say that it's continuous on that interval. And the way we can do that is by only looking at the right-hand limit at 0 and the left-hand limit at 1. That is only looking inside the interval when we're thinking about the endpoints. And Larson, Hostetler, Edwards, 1998, also defined continuity on half-open intervals. It's just kind of a casual, we can do the same thing that we did for closed intervals for these half-open intervals. 7 of the texts that I looked at defined continuity on arbitrary intervals, but in a way that wasn't as careful about endpoints. Usually it's just some sort of definition as simple as this one from Marsden and Weinstein, 1985. A function is said to be continuous on a given interval if it is continuous at every point on that interval. So this definition applies to any sort of interval, and in particular, if we look back at our characteristic function for the closed interval from 0 to 1, it wouldn't say that this function is continuous on the closed interval from 0 to 1, since it's not continuous at 0 or 1, which are points in that closed interval. So this condition here for continuity on an interval is a stricter condition. It means that fewer functions will meet the hypotheses of the intermediate value theorem and extreme value theorem, and Marsden and Weinstein in 1985 goes on to note that. In a footnote for the intermediate value theorem, they say, our definition of continuity on the closed interval from A to B assumes that f is defined near each point at x bar of AB, including the endpoints, and that the limit as x approaches x bar of f of x is f of x bar, so continuity at those points. Actually, at the endpoints, it is enough to assume that the one-sided limits from inside the interval exist, rather than the two-sided ones. So they're aware of this limitation and make explicit note of it. But 5 of the 6 other texts that fall into this category fall into that awkward second category in terms of continuity at a point, where they make explicit exceptions for continuity at left and right-hand endpoints of the function's domain. So those texts, even though they wouldn't consider our example function here to be continuous on the closed interval from 0 to 1, would consider this function here to be continuous on the closed interval from 0 to 1, because they would say that for this function it is continuous at 0 and is continuous at 1, and therefore continuous at all points in the closed interval from 0 to 1. So I feel like they're approaching this from a slightly different perspective than Marsden and Weinstein. Then we have a few texts that don't define continuity on half-open intervals. I found 2 that use the handed continuity definition for continuity on closed intervals, but only define continuity on closed or open intervals. I found 2 that use the handed continuity definition of continuous on a closed interval and only defined continuity on closed intervals. And 1 text that only defined continuity on closed intervals, but just as being continuous at every point of the interval, so not being as careful with the endpoints. In all, the texts seem to focus on continuity on closed intervals, as we might expect as a kind of a setup for the continuity theorems, with other types of intervals being less common but not uncommon. And the texts that did define continuity on closed intervals seemed about evenly split between requiring full continuity at the endpoints or just the appropriate handed continuity from the interior of the interval. Of course, if we're going to talk about confusion involving continuity in Calc 1, I have to mention the issue of continuous functions with points of discontinuity. The typical definition of continuous function is a function that is continuous at every point in its domain. But what this means is that functions with points of discontinuity outside their domains, like 1 over x and the absolute value of x over x, which both have points of discontinuity at 0, both of these functions are considered continuous functions. Because they're not defined. Their domain doesn't include x equals 0. And not everybody is thrilled about this. I personally appreciate this convention because of its practicality. One of the big goals of talking about continuity is to be able to classify a wide range of functions where we can easily calculate limits by plugging into the function. This convention allows us to universally say if two functions are continuous, then their quotient is continuous, even if the denominator is sometimes 0. Compared to requiring continuity at all real points, we have a bigger collection of continuous functions, and it's easier to identify continuous functions. And the only price we have to pay is that sometimes plugging in will fail, in which case we'll need other tools for assessing those limits. But this does confuse students, so a common response is to simply not define continuous function at all. I'm including here a bunch of texts I found that talk about continuous functions, that use the term continuous function, but don't actually define that term anywhere. I was actually surprised to find a couple of texts that required continuous functions to be defined everywhere. But here they are. Apparently the convention of defining a continuous function as a function that's continuous everywhere in its domain and who cares about other points isn't quite the universal standard that I thought it was. So what can we conclude from all of this? Well, it's very tempting to think of mathematics as absolute, that all mathematicians should agree on all facts. This is, after all, what allows mathematicians to engage in fruitful collaboration, even across time. However, mathematics is fundamentally an activity of mathematicians, and so we see all over the place the arbitrariness, the humanity of mathematicians, our humanity. And one place we see this is in our choice of definitions. We don't just magically all agree on what continuity at a point should mean. We have individual mathematicians or groups of mathematicians looking at what has been done before and writing texts in a social process that usually converges, ultimately, on having a single definition for any one particular mathematical term. The strength and speed of that convergence is plenty random, but it's affected by things like whether there's a single definitive text on the subject, or how important it is that everyone agree, or whether there's a definition that's substantially nicer than the others. Harper points out, in the case of continuity at a point, the situation isn't particularly urgent or even noticeable because continuity at a point is mainly just there to help us define continuity on intervals, which we then use in the hypotheses of theorems like the intermediate value theorem, and to define continuity of functions, which lets us calculate limits quickly. Although, to be fair, we've also just seen two distinct notions of continuity on a closed interval, so there's probably some other forces at work as well. Another consequence of mathematicians being human is that they make mistakes sometimes. We've seen a number of Calc 1 textbooks with various inconsistencies in them, but I don't mean to shame them. I've certainly made plenty of mistakes in stuff I've published. And finally, a mathematical lesson that partial functions, functions that aren't defined everywhere, are a real nuisance to work with. The whole disagreement on continuity at a point is what to do when the function isn't defined near that point. For total functions, functions that are defined everywhere, all three of our continuity at a point conventions agree. So thanks for watching. Let me know in the comments if you know of some other definition that mathematicians disagree on in some substantial way. Bonus points if you can find some disagreement that's not already well known. Also, let me know if you have any questions or comments about this video, and be kind to each other.